Welcome to the Explainer. You know, our gut feelings about probability, they can be surprisingly, shockingly wrong. Today, we're going to look at a mathematical tool that proves it, and, more importantly, shows us how to get it right.
All right, let's just jump right in with the classic head scratcher. So, picture this. You go for a medical test, right? It's 90% accurate, and you test positive. Now, what's your first reaction? You probably think, okay, there's a 90% chance I have this disease. Makes sense, right? Well, hold on, because our intuition is about to take a serious hit.
So here's the setup, and this is where it gets really interesting. Yeah, the test is 90% accurate. That part's true. But here's the kicker. The detail our brains just love to gloss over, the disease itself is super rare. It only affects 1% of the entire population. This little number, this base rate, it's the key to the whole thing. It completely flips the script.
So, how do we make sense of this? How do we untangle this puzzle? Well, we need a tool for the job, and that tool is called Bayes' Theorem. You can think of it as a formal, logical way to update our beliefs when we get new information. Okay, here it is, the formula itself. And I know, it looks a little intimidating with all the P's and brackets, but don't worry, we're going to walk through this step by step. Seriously, don't think of it as a scary math equation. Think of it more like a recipe for taking what you already believe, adding in a dash of new evidence, and cooking up a new, much more accurate belief. So let's start with the first ingredient, P of A, which is just a fancy name for the prior probability. This is basically our starting point. What do we believe before we have any new evidence? In this medical case, it's just the odds of anyone having the disease in the first place, which is that tiny 1%. That's our prior. All right, next up, we have the likelihood. This part, P of B given A, is all about the strength of our new evidence. It asks a really specific question. Assuming I have the disease, what are the chances the test would catch it? Well, the test is 90% accurate, so that's our answer. The likelihood is 90%.
And finally, this is what it's all about, the posterior probability, P of A given B. This is the big reveal. It's our updated belief, the actual probability that we have the disease given that positive test result. This is the number we've been working towards.
Okay, we've got all our ingredients. Let's plug them into the recipe and see what we get. Time to solve this thing.
Now this is the really critical part. See, it's tempting to only think about the test catching the disease, the true positives. But we have to remember the other side of the coin. False positives. You know, all the perfectly healthy people who get a positive result by mistake. That bottom part of the formula, the denominator, that's what it's doing. It's figuring out the total chance of anyone, sick or healthy, getting a positive result. It's the whole picture. And here we go, the answer. After running the numbers, the actual chance you have the disease is only about 8.33%. Wow, just let that sink in. Not 90%. 8.33. That is a huge difference from what our gut told us, right? So what on earth is going on? Why is it so low? It all circles back to that 1% base rate. The disease is just so rare. Think about it. You have a massive group of healthy people, 99% of them, and a tiny group of sick people. Even a small error rate, like 10%, applied to that huge healthy group creates a big pile of false positives. In fact, that pile of false alarms ends up being bigger than the pile of actual correct positives from the sick group. Okay, so this is way more than just a cool medical brain teaser. This very same logic is the engine behind a super useful tool in machine learning. With just one little tweak, a simplification really, this theorem becomes something called the naive Bayes classifier.
And why naive? Well, it's called naive because it makes a kind of bold, simple-minded assumption. It pretends that all the pieces of evidence it's looking at are totally independent of each other. Like the word free in an email has nothing to do with the word money. Now, in the real world, that's almost never true. But here's the crazy part. Even with that naive assumption, the algorithm works surprisingly, and I mean surprisingly well.
You see this in action every single day with your email spam filter. It's the perfect example. The filter gets trained on a ton of emails, right? It learns the probability that a word like, say, free or a win will pop up in a spam email compared to a normal one. So when a new email lands in your inbox, the filter looks at all the words, multiplies their individual spam probabilities together, and calculates that final posterior probability, the chance that this email is junk.
And it's not just one tool. It's more like a whole toolkit. There are a few different flavors of naive Bayes, and you pick the right one for the job. You've got Gaussian for when you're dealing with continuous data like measurements. Then there's multinomial, which is perfect for things like counting words in a document. And Bernoulli is for when the question is just a simple yes or no. Is this word here or not?
So we've seen how it works, both in theory and in practice. But let's get down to brass tacks. What are the real-world strengths and weaknesses? When should you actually reach for this tool?
The biggest advantages? Oh, they're huge. It's simple and it is fast, like blazing fast. It's easy to build, easy to understand, and it doesn't choke even if you throw a massive data set with tons of features at it. That makes it absolutely perfect for things that need to happen in real time, or just as a great first-pass model to see what's going on in your data. But, of course, there is a flip side. Its greatest strength, that simplicity, is also its biggest weakness. That naive assumption we talked about, that all the features are independent, well, in the real world, that's just often not the case. The words in a sentence are connected, right? So for really complex problems, where the relationships between features are the most important thing, its accuracy can sometimes take a hit.
And one last thing, just to be super clear, it's important to know what Bayes' theorem isn't. The theorem itself is a fundamental rule for updating our beliefs with evidence. It's a way of reasoning. That's different from a technique like, say, cross-validation. Cross-validation isn't about updating beliefs, it's about stress testing a model to see how well it's likely to perform out in the wild on new data. They both play on the same team, but they have very different positions.
So at the end of the day, Bayes' theorem is so much more than just a formula you plug numbers into. It's really a whole mindset. It's a structured way of thinking that forces us to, acknowledge our initial biases, to weigh new evidence properly, and, this is the most important part, to be willing to change our minds. It's a powerful, powerful reminder that sometimes the most obvious answer isn't the right one at all.